In this video, we're going to go over some more of the Chapter 16 problems, the second set that was assigned, and we're going to do about half of these, and then we'll continue on in the next video to finish them up. Okay, so 33, the question in 33 asks, predict the sign delta S of each of the following changes. Okay, so remember, delta S is positive if you get more disorder, more randomness, and it's negative if you become more orderly. Okay, so it's a little bit sort of backwards from how my brain thinks, so I always have to stop and think. All right, so we have 12 gas particles. They're spread out between these two bulbs in the first part, and they're all together in the second part. And it's far less likely. This is more orderly, where they're all in one spot. And so the if this was an arrow here, this would be becoming more orderly, so this is a negative delta S. In the next one, we have a solid, and it's being dissolved. So solid silver chloride is much more orderly than dissolved. These would be two pieces for every one AgCl. It makes two, so that first of all is more disorderly. And then aqueous is always more disorderly than solid, so this is a positive delta S because it's becoming more disordered. This one here, we have 3 moles of gas on the left. We have 2 moles of liquid on the right, if I read this one right. Yep. And so if you're going to liquid, you're becoming more orderly. So this is a minus delta S. And H2O liquid to H2O gas. Gas is the most disordered, so that's a positive delta S. Okay, number 35. Which has the greater entropy? So the greater entropy means that it's a more disordered state. So if we look at graphite and diamond, diamond is a very highly ordered, and so you might not know that, but you should. This is a highly ordered crystal structure, and so the one that has the more disorder would be the graphite. Even though they're both solids, you do have to know a little bit that diamond is a very, very ordered crystal structure. Okay, we have ethanol liquid and ethanol gas, which has the greater disorder, always the gas of two of the same compounds. And we have CO2 solid, which is dry ice, or CO2 gas. CO2 gas would be the more disordered. 39 says, calculate the standard entropy at standard state of CF4. So we want to know this entropy. Given that the change in entropy of this reaction is negative 358 joules per Kelvin. Okay, so it says to look in Appendix 4, and I'm also going to remind you that we got this formula in the reading. It's just like the delta H formula at standard state. So you can find the delta S of a reaction by adding up all of the S's of the products and all of the S's of the reactants and subtracting them. All right, so I just want to point out where this is in your book. Right, so we have Appendix 4 in your book. If I turn to Appendix 4, it's these tables. And so you can go down, like for example, F2 is over here, right? So F2 gas has a delta S of 203. So the delta H, the delta G, and the delta S are all in this table. And remember, I pointed this out on the last video, the delta H and the delta G are in kilojoules. The S is in joules. It's very important that you switch one of these to the other unit so that you can do the addition if you're combining delta H's and delta G's. Okay, so back to our problem here. So I looked up in the appendix and I just sort of wrote down my numbers that I need. These are the S values out of that appendix. So the delta S of the reaction is given. That's this. So we're going to plug in negative 358, and that's joules per Kelvin, equals the sum of the products minus the sum of the reactants. Okay, so the products, we have 2, and then we have the S of CF4, plus 1, and the S of H2. I'm just going to write it out, and then I'll plug the numbers in. Minus reactants, 1 S of the C2H2, plus 4 S of the F2. So negative 358 equals, I looked these up. This one here is the one that I don't know, so I'm going to leave that, 2S of CF4 plus, and technically these should all have their standard states because that's the appendix values. The S of the H2 at standard state is 131 joules per mole Kelvin. Minus, so I'm going to put these in parentheses still just because a lot of people lose this negative sign. 1 of the C2H2, so that's 201 plus 4 times the F2, and the F2 was 203 in the appendix. Okay, and you have to make sure that you get the right state when you're looking in the appendix. So minus 358 is equal to 2 times the S of CF4, that's what we're looking for, plus 131 minus, and so I'm going to do what's in this parentheses first, 201 plus 4 times 203, 1013. And now I can combine the 131. So I'm going to do minus 1013 plus 131. And I get negative 358 equals, move this up a little bit, 2 times the standard entropy of CF4 minus 882. And so then I'll plus the 882 to both sides. And so 882 minus 358, or minus 358 plus 882 is 524, and that equals 2 times the standard entropy of CF4. And then we divide both sides by 2, and we get that the standard entropy of CF4 is equal to 262 joules per mole Kelvin. Okay, so that's number 39. Now we'll go to number, and by the way, all of these have been uploaded onto Classroom in a PDF. So now we're going to go to 41. 41's a little tricky, so I just want to spend a couple minutes thinking about it. It says it's quite common for a solid to change from one structure to another below its melting point. For example, sulfur undergoes a phase change from rhombic, so sulfur rhombic, to, let's see, phase change from the rhombic crystal structure to the monoclinic. Okay, and you don't need to know this. If you take more science in college, you'll get to the shapes. This is more of a college level term here, but it's just the different shape of the solid, like diamond and graphite are a different shape. And it says it does that above 95 degrees, but below the melting point. So I just want to look at the phase, the heating curve graph again, just to see where we are on it. And it asks you to predict the sign of delta H and predict the sign of delta S. We're trying to predict the signs of these two. Okay, so this is the melting point here. We're going to be above 95 degrees, but below the melting point. So I'm going to put 95 degrees Celsius somewhere below the melting point. This is the solid region, right? So we're starting below 95 degrees, and we have S rhombic here somewhere, okay? So we have like the rhombic structure is somewhere below the 95. And what we're doing is we're adding energy to this solid. So remember, this whole thing, this is solid. So we have, a piece of solid sulfur, and we're heating it up. We're adding energy to it. And as we add energy to it, we're going across this axis, that's the energy axis. The temperature of the solid is getting warmer. Anytime you increase the temperature of a substance, you increase its randomness because the molecules are going to be able to move more, right? So if I'm increasing the randomness, that means I must be increasing the entropy. So I go from this version of the solid, and at 95 degrees Celsius, when I get above that, I'm at the monoclinic version, but I'm still a solid. I haven't reached the melting point. So when I go up the heating curve, remember, when you're going up the heating curve, that means that you're putting energy in. That means that your delta H is positive. It's an endothermic reaction. It's taking energy from the outside to get heated. So both of these would be positive in this case. And that's a very good conceptual question to think about. Do you understand that heating curve well enough to rationalize through that? Number 43, consider the reaction. We want to know when two oxygen gas atoms form one oxygen gas molecule, what's the sign of delta H and delta S? So let's just think about it. This has two oxygen atoms floating around. On this side, we have two oxygen atoms with a double bond between them, right? That's O2. I'm going from 2 moles of gas to 1 mole of gas. If I reduce the number of moles of gas, that means I become more orderly, so delta S has to be negative for this problem. I'm becoming more orderly. 2 moles of gas is more disordered than 1 mole of gas. Now, in terms of delta H, remember, this is a very important concept. Forming bonds is exothermic. We talked about a graph that looked like this a while ago, that if you had two hydrogen atoms and you brought them closer together, they went down into this place, and this was the bond length, right? So this was the radius between the two atoms, and this was an energy axis, and this was where the bond formed, when it was down at this very low spot. So forming a bond releases energy. And you can rationalize that because in order to break a bond, you have to put the energy in. Remember, we talk about breaking a bond, right? So breaking a bond is endothermic. Forming a bond is exothermic. And so we have delta H is negative. And then it says, at high or low temperatures, is it more spontaneous? So remember, that's the delta G equation. Delta G is equal to delta H minus T delta S. And delta G is negative for spontaneous reactions. Right? Now delta H is negative and delta S is negative. So I'm just going to put in my signs here, right? So if delta S is negative, and this is a negative times a negative, this becomes a positive value. So the bigger the temperature, the more positive I'm adding to this negative. So the less likely with high temperatures, right? If the temperature's high, then this side, this plus value over here is bigger, and that's going to make it less likely that delta G will be negative. And so that means at low temperatures, will be most spontaneous. So at low temperatures, it's going to be more spontaneous. Okay, and then I think I have one more that we can do together. I'm going to do 45 separate because it really takes a little bit of time to do those 4 problems. So let's take a look at number 51. And 51 is a Hess's law problem. So if we do 51, it says 2H2 gas plus carbon solid is forms CH4 gas, and the delta G for this is negative 51 kilojoules. And then the next equation is 2H2 gas plus O2 gas makes 2H2O liquid. And the Gibbs free energy for this one is negative 474 kilojoules. And then the third equation is C solid plus O2 gas makes CO2 gas. And the Gibbs free energy for this one is minus 394 kilojoules. And what we want is calculate the delta G for CH4 gas plus 2O2 gas makes CO2 gas plus 2H2O liquid. And I want the delta G for that. Okay, so this is a lot like the Hess's law problems. So I have these 3 equations and I have to manipulate them in order to get this equation down here. So the first one I'm going to look is CH4. CH4 is here and nowhere else. So that means that this reaction has to be reversed. So I'm just going to reverse it and put it down here. CH4 gas makes 2H2 gas plus carbon solid, and when I reverse it, like in Hess's law, I change the sign on the Gibbs free energy. Okay, so now I don't need this one anymore. I've reversed it and it's here. And now I think we're lucky because I think that might be all we have to do, because now I have my CH4, that's correct. If I add these up, I probably should have lined up my arrows, right? So I'm looking at the 2 sides of these arrows. So on this side, when I add all 3 of these equations, I get CH4 gas plus 2H2 gas, right? Plus, there's two O's on this side, 2O2 gas, and plus carbon solid. And that makes, on the other side, 2H2O liquid plus CO2 gas plus 2H2 gas, sorry, I'm going to wrap around here, plus carbon solid. So if I just add both sides of these three equations up, that's what I get. And I cross out what's on both sides, so the 2H2 crosses out and the carbon solid crosses out, and I'm left with the equation I wanted, CH4 gas, 2O2 gas, 2H2O liquid, and CO2 gas. And so what that means is if I add up these delta G's, I didn't have to multiply anything, I just reversed one equation. And so if we add those up, we get negative 474 plus negative 394 plus 51, and we get a delta G for this equation is equal to negative 817 kilojoules per mole, and that means because it's negative, it would be spontaneous if they asked you that question. Okay, and that's it for the first part of these questions, and I'll come back with another movie to show you the rest.